Hi, now, we will discuss technologies of repair of wind turbine blades. We will discuss the following topics. State of the art of the repair technologies. Our approach. Testing of repaired samples. Microscopic analysis. Conclusions. How and why the wind turbine blades fail. Wind turbine blades are subject to complex environmental and mechanical loading during their service time. But they can also fail due to extraordinary events like transportation damage, lightning strikes, bird impact. Several regions of blades are especially susceptible to degradation during service time. Leading edges of blades are subject to rain and hail erosion. Transitional regions, for instance, ply drop, area of transition from cylinder to aerofoil, tend to show delamination of composites. Adhesive joints can debond, and it can trigger buckling of structure. This failure mechanism can be observed in trailing edge or at web to spar joint. DTU Wind and our colleagues from Indian Institute of Wind Energy carried out survey among service teams on frequency of observation of different failure mechanisms. Leading edge erosion is most often observed mechanism over first service years. Mechanisms of structural failure of wind turbine blades include structural collapse and buckling, delamination in tapered areas, and ply drops, adhesive bond degradation, and buckling in trailing edge and skin spar. Generally, the blade damage mechanisms can be grouped into surface damage, non-structural cracks, and structural damage. They require, correspondingly, different repair technologies. For instance, new painting or shells for erosion. Injection for delamination, scarf repair for structural cracks. Levelized cost of energy depend on the operating expenses, and high repair costs increase the operating expenses of wind turbines. Here, you can see a formula to estimate the contribution of blade repair to the costs of wind energy. The parameters related to repair technology include duration of work, size of team, equipment and materials costs, and the frequency of repairs. But which blade repair technology ensures both lowest costs, longest post-repair lifetime, and minimum repair frequency? Here, we want to investigate it. Two questions are considered. How to improve repair of wind turbine blades? And what are weak spots of different repair technologies? To investigate different repair technologies, laminate plates were damaged, and then repaired by experienced technician. Then, the plates were tested, and microscopic analysis of structures was carried out. The following technologies have been studied. Hand layup lamination, vacuum repair with hand layup, vacuum repair with infusion, ultraviolet repair with handheld, portable, continuous UV spectrum curing, ultraviolet repair, stationary device, high-temperature thermal curing with vacuum. The technologies were selected by practical repair team. Material costs and time for repair were estimated by the repair team as well. Then, the samples were tested under static and cyclic loading. Here, you can see the repaired plate and tensile samples. This table shows the young medullae and critical stresses for different samples. Let us compare them in relative values. We can see that all the technologies give relative good quality of repair under static loading. Technologies with application of vacuum lead to stiffer repaired structures and to lower maximum stress. High temperature curing leads to softer structures, but with higher maximum stress. Ultraviolet curing technologies ensure average stiffness and high strength. Further, fatigue testing was carried out. Due to difficulties of testing, in COVID times, only fatigue testing for peak strain 0.5% was carried out. Here, we can see that vacuum repair with hand layup shows the lowest performance. Even hand layup is better than vacuum repair with infusion. Stationary UV curing repair system shows average lifetime and high variability. Handheld UV curing shows the best lifetime. High temperature curing shows average level. It was observed that the samples tend to bend after testing. We assume that the bending of samples is a result of residual stresses caused by different heatings in scarf and parent laminate. The curvature of samples were measured using a special software. The three-point circle was defined, and diameter was calculated automatically. Here, we compare the curvature of samples after testing, and their relative strength. We can see some correlation. It can be assumed that technologies which create residual stresses lead also to early failure. As said, the curvature of samples reflects the internal residual stresses. In order to analyze the microscopic effects of different curing technologies, the samples were investigated by X-ray tomography. The samples were scanned with a polychromatic beam using Nikon 225 and a Zeiss X-Radia Versa scanner. The reconstructions were performed using a standard filtered back projection, resulting in a voxel size of 9.64 micrometers. The reconstructions were segmented, using a constant threshold, to separate the black air bubbles from the gray epoxy and the white fibers. Here, you can see the void density and distribution for 3 cases. Vacuum repair with hand layup. Hand layup. Handheld ultraviolet curing. It is of interest that vacuum repair with hand layup give very high void density, almost 5%, and a lot of elongated voids. Handheld ultraviolet curing leads also to relative high void density, almost 2%, and many round voids. Now, void density and distribution for 2 more cases. High temperature curing and stationary ultraviolet curing. In both cases, the void content is acceptable, about 0.5%, and both round and elongated voids are observed. In order to visualize the void shape distribution, different voids were marked with different colors. Here, voids in resin are marked in red, while voids or air bubbles near fibers are marked in turquoise color. Many small air bubbles in the bundles, and large air bubbles between bundles horizontally, are seen after vacuum repair with hand layup. Hand layup lamination leads to less small air bubbles in the bundles, and a few large and more spherical air bubbles. Handheld UV technology leads to both small and medium-sized air bubbles in the bundles, and large spherical air bubbles between bundles. Microcracks were identified in samples by inspecting virtual cross-sections through the tomographic reconstructions. Here, you can see cracks identified in high-temperature cured samples. The defects were found in parent laminate. In handheld UV cured samples, microcracks were seen in the scarf. Let us summarize the observations. Vacuum technologies ensure stiff adhesives with low maximum stress. UV technologies lead to average stiffness and rather high strength. High temperature curing leads to soft adhesive with high maximum stress. Vacuum technologies leaves a lot of voids in adhesive, more than all other technologies. Fatigue results follow the trend of porosity, namely, vacuum technologies show lowest lifetime, and both UV and high temperature curing show average results. Some repair technique might introduce damage in parent composite, in some cases, also create residual stresses. Porosity plays an important role for post-repair reliability of blades. Can we simulate void formation and their influence? We at DTU developed a multi-scale computational model of repaired blade, taking into account the scarf geometry, and also porosity in the adhesive. As expected, larger voids increase stress concentration in adhesives, and shorten the post-repair lifetime. In the joint work of Indian Institute of Technology Delhi and DTU, the kinetics, growth and formation of voids were simulated. This work will be presented later today. Here, you can see the list of our publications in this area. Feel free to drop me a line if you need some of them. We are grateful to the Ministry of Foreign Affairs of Denmark and to Danita Foundation for the support via the Maintainer G project. Thank you for your attention.